Welcome to INSITECT. Today we are talking about CCTV surveillance systems, cameras, video, and security. Okay, let's unpack this enormous topic. When the average person thinks of CCTV, they're probably still picturing a fuzzy picture of a potential theft.
From an ancient convenience store, right?
Yes.
Maybe captured on a VCR.
Exactly. But our source material makes it abundantly clear that modern surveillance systems they're no longer just passive video archives. We are deep into a highly sophisticated, data-driven ecosystem.
A completely different world.
So our mission today is a rigorous deep dive into this technology, moving far beyond that simple idea of a camera recording a video stream. We're going to be dissecting the whole stack, from the physics of the lens to the complexity of the AI that governs it.
And, crucially, the compliance framework. The part that's required to make it all legally viable.
That's it.
That's really the key distinction. The core definition of CCTV closed-circuit television, it remains technically simple, right? It's a system using camera video for security monitoring. But its function today is, well, it's almost unrecognizable compared to the analog era. It's transformed from, like you said, a tape recorder into this coordinated layer of protection and visibility.
It's a whole new paradigm.
It is.
Yeah.
We're talking about combining high-resolution camera hardware, strategic video recording, advanced security monitoring, and increasingly integration into the core business infrastructure.
Yeah.
It is now fundamentally a tool for data-driven risk control.
Data-driven risk control, that's a great way to put it. It's essential for liability management.
Exactly.
And the most critical evolution that our sources really highlight is that foundational shift in architecture, right? I mean, we're talking about the retirement of those older analog systems, the ones that relied on coaxial cabling and, dedicated DVRs.
That shift is paramount
Yeah.
because it changed the capability entirely. We'd have overwhelmingly transitioned to IP-based architectures, internet protocol.
See, analog systems were just so constrained. Physical wiring limits, proprietary formats, you couldn't really scale them. The move to IP enables seamless remote access, which is huge for any company with more than one site.
Of course.
But more importantly, it unlocks intelligent analytics and broad platform integration. This move from a proprietary closed system to an open networked infrastructure is what allows CCTV to act as a flexible analytical engine.
So for you listening to this, the goal is to fully understand not just the sophisticated hardware, but the complex infrastructure and the compliance that's necessary to manage these systems effectively. Because, as we're about to see, buying the best camera in the world means nothing if your network chokes on the data.
Or if your legal department says you can't use the footage.
Exactly. All right, let's start literally at the edge, the camera itself. The reliability of surveillance, as security evidence, hinges entirely on the quality of what that camera captures and how it captures it.
It all starts there. If you get garbage in, you get garbage out. So we really need to understand the material choices that dictate forensic success. And beginning with image quality fundamentals, let's focus on the sensor. Our sources confirm the market is it's dominated by CMOS sensors.
Yeah, and this isn't just a technical preference. It's a strategic choice.
Why is that?
It's primarily due to their low power consumption, which is a huge deal when you're powering hundreds of cameras over Ethernet. And it's also about the ability to integrate processing functions directly onto the chip itself.
Which is essential for all the modern AI on the edge capabilities we're hearing about.
That's right. You can do some of the analytics right there in the camera before the video even hits the network.
Okay, but the real decision point, it seems, is sensor size. We often hear these specs like 13-inch versus 12.8-inch. It seems like a tiny difference.
It sounds tiny, but it dictates everything about low-light performance. Generally, a physically larger sensor just has a greater surface area to capture photons, to capture light.
So if you have a poorly lit warehouse or, say, a shadowed parking lot,
then choosing a camera with that larger sensor means the image will be cleaner, less noisy when darkness falls. And that directly impacts your ability to actually make an identification of a person or a license plate.
Which is the ultimate purpose of the forensic evidence, right?
It's the whole point.
And then there's that classic tension, resolution versus bandwidth. Everyone wants higher resolution.
Of course. Resolution defines the detail. A standard 2-megapixel camera gives you full HD, so 1920 by 1080, which is usually considered the minimum for reliable identification these days.
But if you jump to 4K, which is 8 megapixels, you gain so much more detail, enough perhaps to read a distant license plate that would just be a blur on a 1080p camera.
But that jump, that glorious detail, comes with a massive infrastructure cost. It's not a free upgrade.
Massive.
Well, think about it. 4 times the detail means you are instantly increasing your required bandwidth and storage capacity by a factor of at least 3, sometimes more, depending on the compression you're using. So we'll talk about storage later, but this is the first hard trade-off you have to make. Do you absolutely need that maximum detail, or can your network handle the massive data pipe needed for hundreds of 4K streams running at the same time?
That balancing act really dictates the budget for the entire project, doesn't it?
It's one of the first questions you have to answer.
Okay, so once the light hits the sensor, the camera's internal processing takes over. Our sources highlight these critical features like wide dynamic range, or WDR, and noise reduction.
Right. Noise reduction, for example, is what algorithms use to smooth out that grainy appearance. You know, those little artifacts that appear in deep low-light footage. It cleans up the image.
But WDR seems, I don't know, even more critical for evidence.
WDR is absolutely essential. Imagine a camera pointed at an entrance door or a big window. If it's daytime, the scene inside might be perfectly exposed, but the sunlit view outside is completely blown out. It's just a whitewash.
And if you expose for the outside.
Then the people entering the door are just black silhouettes. You can't see their faces. The key forensic evidence is useless.
So how does WDR solve this?
Wide dynamic range technology. It solves this by taking multiple rapid exposures at the same time. One is optimized for the bright area, one for the dark, and then it intelligently stitches them together into a single balanced image. Without good WDR, a person's face could be completely lost.
Moving from the sensor to the lens, the physical choices here determine how you deploy the camera and what it ultimately sees. We have, what, 3 main categories: fixed, varifocal, and motorized.
That's right. Fixed lenses are the simplest, most cost-effective. They have a set focal length. They provide very predictable coverage. They're ideal for, a hallway or a small lobby where things don't change.
And varifocal.
Varifocal lenses offer flexibility, but only during installation. The technician can manually adjust the zoom and focus on site to really fine-tune the field of view. But once it's set, it's set.
But the motorized lens is the true architectural benefit for long-term management, isn't it? Because it allows for remote adjustment through the video management system, the VMS.
It's a game changer for maintenance. The field of view can be adjusted months or even years later without setting a technician up on a ladder with a laptop. That's a significant operational cost saving over the life of the system.
Okay, now let's address the elephant in the room. Pan-tilt-zoom cameras, PTZs.
Ah, yes. They are seductive. They offer mechanical movement, powerful optical zoom, which is excellent for control rooms with active operators who need to track a subject across a large area.
But I sense a but coming.
A big but. And here's our skepticism point from the sources. PTZ cameras inherently only view one location at a time. The moment an operator focuses on a moving subject in the west corner of a parking lot.
They've created a massive blind spot in the north and south corners.
Exactly. They are tools for active investigation, but they cannot guarantee continuous coverage of a wide area. And if that continuous coverage is a regulatory or legal requirement, relying on a PTZ makes you liable.
So how do we solve that coverage problem without relying on a human operator constantly moving the camera around?
We use cameras that are specifically designed for continuous wide field of view capture. And that's where multi-sensor cameras just excel.
How do those work?
They integrate multiple fixed lenses and sensors, maybe 4 or 5 megapixel sensors, into a single camera housing to provide a continuous 180-degree or even 360-degree view. And crucially, there are no moving parts.
And what about panoramic cameras with fisheye lenses? They capture entire rooms or intersections.
They do, and they're another great solution.
But I've seen fisheye footage, and it looks like it was shot through a peephole. It's incredibly distorted.
You're right, it is, and that's the technical caveat. They capture the whole room, but the raw image is curved and distorted. The usability relies entirely on the software dewarping capability that's built into the VMS.
So the software flattens the image out.
Exactly. It takes that distorted image and flattens it into usable rectangular views for the operators. Some systems even allow them to digitally pan and zoom within that fixed 360-degree view without sacrificing coverage anywhere else.
Okay, let's do a deep dive now into some specialized imaging. I want to focus on techniques that defy typical visible light limitations, particularly the combination of thermal and radar fusion.
This is where things get really interesting. Thermal cameras are fundamentally different from normal cameras. They don't see light at all. They detect infrared radiation based on temperature differences.
Which makes them perfect for
For complete darkness, heavy fog, smoke, or heavy rain. environments where standard visible light cameras are completely useless. They are absolutely essential for remote perimeter security or harsh industrial sites.
But thermal cameras are prone to false alarms, right? I mean, a deer walking by or even a car engine that's cooling down could trigger an alert.
Exactly. And that's where sensor fusion comes in. Thermal alone is great for detecting heat. But by combining thermal imaging with radar, you dramatically improve the accuracy and the specificity of the alert.
How does the radar help?
Radar provides precise range and velocity data. It knows the exact distance and speed of the object. So the radar detects an object moving at 5 miles per hour at 100 meters.
And the thermal confirms it has a human-like heat signature.
Exactly. The fusion process cross-references the two data points and drastically reduces those frustrating and costly false alarms caused by environmental factors. A plastic bag blowing in the wind or a small animal crossing the fence line. It's the required engineering step to reduce that operational noise.
Before we leave the hardware, let's talk practical durability. Cameras, especially the ones outside, are subject to the elements and sometimes, well, to malicious actors.
This is the essential layer of protection, environmental protection. If a camera fails because of rain or someone throws a rock at it, all your advanced analytics are meaningless.
So our sources stress the necessity of IP-rated enclosures. What does that mean in practice?
An IP66 rating, for instance, means the enclosure provides complete protection against dust ingress and can resist powerful jets of water. It's really the baseline for reliable outdoor use in most climates.
And then there's the question of, physical assault on the camera itself, vandalism.
That requires the IK rating, which signifies vandal resistance. An IK10 housing is the gold standard here. It means the camera can withstand an impact equivalent to 20 joules.
Which is like what?
Think of a baseball bat or a well-aimed rock. This protection ensures that if a camera is placed within physical reach, like in a subway station or a low-hanging eave, the dome and housing can survive targeted physical damage, preserving the integrity of the footage until law enforcement arrives.
So these durability factors, they really must be non-negotiable considerations in the capital expenditure plan.
They have to be. Otherwise, you're just replacing cameras every year.
Okay, we've nailed the edge device. Now we move inside the walls and into the infrastructure. This is the IP backbone. If the network fails, the cameras become, very expensive paperweights.
It's the central nervous system of the entire operation.
So we must analyze the critical requirements that guarantee continuous video feed integrity. Let's start with what I think is a revolutionary aspect of modern surveillance infrastructure: power over Ethernet, or PoE.
Oh, absolutely. It's an elegant solution. It delivers both data and electrical power over a single standard Ethernet cable. It massively simplifies installation and saves a ton on electrical contracting costs.
But simple isn't always easy, is it? You have to understand the PoE standards to make sure your devices actually function.
That's the catch. 802.3AF is the basic standard. It provides up to 15.4 watts per port. That's fine for a small fixed camera with minimal processing and no special features.
But many modern cameras have components that require a lot more power, right?
Absolutely. If your high-resolution cameras incorporate things like internal fans for cooling, integrated heaters for cold environments, or strong IR illuminators for night vision, you need the next standard up.
Which is?
802.3 Air, or PoE plus Molbaya. That boosts the power available to 30 watts per port. And for the really heavy hitters, those PTZ domes we talked about, or the advanced multi-sensor units, you need the latest standard, 802.3 BT, which can deliver up to 90 watts.
And this brings us to a massive, and I mean massive, failure point that our sources say many systems integrators overlook: power budgeting.
This is so critical.
Yeah.
The network switch itself has a total power budget. It must provide sufficient total power capacity to supply all the connected devices, especially at their peak demand.
Can you give us an example?
Sure. Imagine a university campus installation in a northern state. If it's a freezing night and all 100 outdoor cameras kick on their internal heaters simultaneously, the total power draw can spike dramatically.
And if the switch's total power budget is exceeded,
The switch will start shutting down ports to protect itself. The lowest priority cameras will simply stop working, or they'll get stuck in a loop of repeatedly rebooting. Failure to calculate that total power budget reliably is one of the most common causes of intermittent surveillance outages.
Okay, so when we talk network design, our sources are adamant about one point: network segmentation. Why is it so crucial to use dedicated infrastructure to separate that video traffic from the general corporate network?
The reasons are twofold: performance and security.
Let's start with performance.
On the performance side, video streams, particularly high-resolution ones, they consume immense constant bandwidth. If you simply plug 100 cameras into your regular office network, that traffic will quickly choke the lines. It'll severely slow down email, VoIP, and all your other critical business operations.
So you use dedicated switches and VLAN segmentation.
Exactly. You isolate the video traffic onto its own virtual network, ensuring it doesn't impact your business services.
And the security side.
Isolating the camera traffic onto a specific surveillance VLAN that only the recording servers can access is just, well, it's mandatory cybersecurity practice. If a general corporate laptop gets compromised by malware, that malware can't easily jump across the segmented network to compromise or shut down your cameras. It provides a robust layer of defense against that kind of internal lateral movement.
Physical infrastructure presents another challenge. Standard copper Ethernet has a hard range limit. It's what, 100 meters for reliable power and data?
That's right, about 328 feet. And that's very restrictive in campus environments, large warehouses, or any kind of multi-building site.
So the solutions require shifting away from copper?
For long distances, you absolutely must move to fiber optic connections. Single-mode fiber, for example, can easily support runs exceeding 10 kilometers. And a key benefit of fiber, especially when you're bridging between buildings that have different electrical power sources, is that it helps eliminate something called ground loop issues.
Wait, what is a ground loop issue and why does fiber solve it? That's a term that gets thrown around a lot in IT.
So a ground loop is essentially electrical noise. It happens when two pieces of equipment, say the camera in one building and the recording server in another, are connected to different electrical outlets that have slight variations in their grounding potential.
And that voltage difference causes problems.
That difference in voltage travels along the copper shield of the Ethernet cable, creating interference. It often manifests as a hum or lines in an analog signal or just general signal degradation and packet loss in a digital one.
And because fiber uses light.
Since fiber optic cables transmit data using pulses of light, not electricity, they completely break that electrical connection. They are immune to it. It eliminates the ground loop entirely and guarantees a clean signal between buildings.
That clarifies the why of fiber. But what about the convenience of going completely wireless? For areas that are just too difficult or expensive to run a cable to, like a remote parking lot gate or a temporary construction site.
We have to maintain a healthy skepticism here, especially when the footage is intended as forensic evidence. Wireless options, point-to-point microwave, or unlicensed 5 gigahertz connections, they certainly exist.
But they have limitations.
Major limitations. They offer lower sustained bandwidth, and they are highly susceptible to interference from other wireless networks, from weather like heavy rain or from physical obstructions. Our sources confirm that wireless often struggles to maintain high-resolution, high-frame-rate feeds reliably.
So it's an option for.
It's an option for low-priority observational streams, but it should really never be the backbone for your mission-critical, high-definition evidence capture.
Okay, moving to quality of service, or QoS. Let's get into the hard numbers. Bandwidth planning is essential for system health. What are the typical demands we should be planning for?
You need to base your infrastructure purchases on reliable planning. A high-quality 1080p camera running at 30 frames per second will typically consume somewhere between 2 to 6 megabits per second, depending on the scene activity and the codec being used.
And if you jump to 4K?
That jumps significantly to maybe 8 to 15 milladps per camera. So the total network load is calculated by multiplying that average byte rate by the number of cameras. Getting this calculation wrong from the start means your network is congested from day one.
And the quality of the video experience relies not just on pure capacity, but on 3 critical and often overlooked metrics.
The 3 enemies of video quality, I call them. First, latency.
Which is the delay.
Right. The delay between the event happening in front of the lens and the operator seeing it on their screen. High latency is catastrophic for live monitoring and makes controlling a PTZ camera completely impossible.
Number 2.
Second, jitter. This is the variation in the packet arrival times. Imagine trying to talk to someone on a bad connection whose voice keeps stuttering and speeding up. That's jitter in a video feed. It causes choppy, unstable playback.
And the third enemy.
Packet loss. This usually results from network congestion or maybe faulty equipment, and it directly degrades image quality by skipping frames or causing that blocky pixelation in the image.
So how do you proactively manage these almost invisible technical issues?
You absolutely must use network management tools. Our sources stress the necessity of using standard IT protocols like SNMP, that's Simple Network Management Protocol, to collect statistics from all your switches and routers.
And the VMS itself should help.
A good VMS should have diagnostic tools that are constantly tracking camera connection status, bitrate, and frame rate. Proactive monitoring isn't a luxury. It prevents those subtle network degradations from turning into critical outages that compromise the integrity of your evidence. Moving up the stack, we arrive at the software layer, the Video Management System, or VMS. This platform is where all that raw data from the cameras is transformed into actionable intelligence, and is where the architecture that protects that data is defined.
Okay, let's break down the VMS structure. The sources talk about the classic client-server model. Walk us through that workflow and why separating those functions is so key for large-scale operations.
The separation is all about workload distribution and maintaining data integrity. The recording servers are the silent workhorses of the system.
They do the heavy lifting.
They connect directly to the cameras, and they handle the continuous heavy-duty tasks, receiving the streams, encoding them if necessary, and writing them to storage 24/7. The client workstations are the operator interfaces. They're the PCs where security staff view live feeds and search through the archives.
And by separating those roles,
By separating them, you ensure that one operator searching 6 months of archives doesn't steal processing power or memory from the recording engine. It guarantees continuous, uninterrupted data capture, which is the most important function.
now, when you're configuring recording, organizations have to decide how much data to keep. We have, continuous recording, which is the brute force method.
Records everything, all the time.
Then there's motion-based recording to conserve space, and event-based recording, which might be triggered by an alarm or an analytic.
Right. But regardless of the type you choose, these choices must align strictly with the organization's retention policies.
And these policies are often non-negotiable legal requirements, aren't they?
They are. For instance, a financial institution is often required by regulators to maintain all footage for a minimum of 90 days. A retail store might only require 30 days. Defining this retention period based on legal, regulatory, and business needs is paramount.
Why paramount?
Because accidental erasure of required footage can lead to massive compliance fines or the inability to defend against a lawsuit.
And for the security teams who are tasked with reviewing what could be immense amounts of footage, efficiency is everything. Our sources emphasize tools that drastically cut down investigation time, like bookmarking, tagging, and metadata filtering.
These features can turn a 6-hour manual video review into a 6-minute targeted search. It's a huge difference. Operators can bookmark relevant footage instantly as it happens, adding notes about the incident.
And tags.
Tags allow them to categorize events by type, slip and fall theft, unauthorized access. But the real accelerator is leveraging metadata from the analytics.
How does that work?
If the system is classifying objects, the operator can filter the archives by specific attributes. They can run a search like, show me all instances of a red truck crossing zone last Tuesday between 2 and 4 p.m., instead of manually scrubbing through hours of footage frame by frame.
Let's shift to the physical storage architecture. Let's start with the distinction between the legacy systems and modern systems, NVR versus DVR.
The distinction really boils down to where the encoding happens. Digital video recorders, DVRs, handle analog cameras. They receive the analog signal over coax cable, and then they digitize and compress it at the recorder.
And network video recorders.
NVRs are built for IP cameras. They simply record the streams that have already been compressed and encoded by the camera itself. Because NVRs are IP-based, they scale far more easily. You just add more network storage capacity. It makes them the standard choice for any modern large-scale installation.
For truly massive archives, we move into enterprise-grade storage solutions. Explain the difference between a SAN and a NAS in this specific surveillance context.
Okay, so this is a cost and performance question. A storage area network, or SAN, provides high-performance, block-level storage. It's extremely fast, very robust. It's ideal for environments with hundreds or thousands of high-resolution cameras that demand instantaneous read-write speeds.
But it's expensive.
Very expensive, and it requires specialized IT staff to manage, often a dedicated storage administrator. Network-attached storage, or NAS, is simpler. It connects via standard Ethernet, making it more cost-effective and much easier to deploy for small to medium sites. The choice really depends on your performance needs, your budget, and your internal IT expertise.
And the physical reliability of all that data relies on RAID technology. That's our safety net against a mechanical disk failure.
RAID is completely non-negotiable for video archives. You have to have it. RAID 5 uses something called parity to protect data against the failure of one single disk in the array. The system can then rebuild the lost data using the remaining drives.
But for massive video archives, RAID 5 might not be enough.
That's right. RAID 6 is often preferred because it increases the redundancy. It can tolerate the simultaneous failure of two disks without any data loss. Furthermore, it's absolutely critical to use surveillance-grade drives.
What's the difference?
These are not standard desktop drives. They are specifically optimized for continuous 247 write operations, that constant stream of data that's inherent to video recording rather than the bursty read-write cycles of a typical desktop PC. They're built for endurance.
Let's talk about resilience at the very edge, the local safety net in case of a network failure. You're talking about edge storage.
Exactly. Edge storage, which is typically an SD card housed directly inside the camera, is a critical component of data integrity. It serves as a brief but crucial buffer.
So if the network switch fails or the connection is temporarily lost,
The cameras continue recording locally to that SD card. Once connectivity is restored, the VMS performs what's called a backfill. It syncs the locally recorded footage from the card back to the central NVR. This prevents those frustrating data gaps that can happen during temporary infrastructure outages.
and this usually works in conjunction with a hybrid storage model, right?
Yes, where you have local high-resolution storage for quick, recent access, combined with cloud archiving for long-term offsite retention and disaster recovery.
Finally, let's tackle data protection and compliance. This is really the legal heartbeat of the system. First, bitrate control, the comparison between the H.264 codec and the newer H.265.
H.264 is the baseline. It's a widely adopted compression standard that works well. But H.265, which is also called high-efficiency video coding, is the modern strategic choice. It achieves a comparable image quality at approximately half the bitrate.
That's a huge saving.
It's not marginal at all. It's the difference between needing 10 hard drives versus 5 hard drives for the same retention period. For an organization that's required to keep footage for years, the decision to migrate to H.265 is a critical cost-saving decision for the storage architect.
And for the evidence to be admissible in court, we need to prove its integrity. How do we prove the footage wasn't tampered with?
This relies on two key components: encryption and digital signatures. Encryption protects the video, both while it's in transit across the network and when it's stored on the server, what we call at rest. It guards against unauthorized viewing.
But the digital signature is the key legal component.
It is. It provides a unique cryptographic fingerprint for that video file the moment it's created. Any modification to the file, even changing a single bit, breaks that signature. It instantly invalidates it. This mechanism maintains the chain of custody and ensures that when you present the footage in legal proceedings, its integrity can be confirmed beyond a reasonable doubt.
This next section, this really represents the true paradigm shift in surveillance. We're moving from a passive archive, it's something you check after an incident has already happened, to active sensing, where the system itself provides real-time alerts and actionable intelligence.
This is the move from reactive to proactive. It's a huge leap.
Let's start with the core analytics functions. The backbone remains pretty simple, right? Basic motion detection and object tracking across frames, but the intelligence comes from how you define the rules.
Precisely. We can define spatial rules. These can trigger alerts when objects cross virtual lines, like a digital tripwire across a property boundary, or when they enter defined restricted zones. These basic rules can automate a huge amount of security monitoring.
And building on that, we move to business intelligence with people and traffic management.
Right. This includes things like people counting, which is essential for retailers who want to measure staffing needs or customer conversion rates, and crowd density measurement, which is a crucial safety application in public venues to prevent dangerous overcrowding situations.
Now, our sources also mention behavior and anomaly detection models. This is the promise of AI identifying things like running, fighting, or aggressive behavior. But this is the place where operationally things get really difficult. This is our second major skepticism point.
It sounds incredibly powerful, and it can be, but implementing it is extremely challenging. Behavior analysis requires the algorithms to first learn what normal behavior is for that specific site, and that can take weeks or months of observation.
And then it flags deviations from that normal.
Exactly. It flags anomalies.
Yeah.
But the operational killer here is the false positive rate. If the algorithm isn't continuously tuned to ignore non-threatening local factors, like a delivery person rushing to make a deadline or specific environmental noise, the security team will be absolutely flooded with false alarms.
Which leads to alert fatigue.
It does, and that can cause them to ignore a genuine threat when it finally happens. This requires continuous human oversight, budget, and a level of tuning that is very often underestimated.
Okay, moving into high-stakes identification. Let's discuss facial recognition. This is highly effective, but it comes loaded with a ton of legal and privacy weight.
It does. Facial recognition identifies and tracks faces, comparing them against databases for uses like frictionless access control or security watch list screening. The critical factors for accuracy are incredibly specific, though.
Such as?
You need high-resolution cameras positioned ideally at eye level or just slightly above. You need them optimized for low-angle capture to get usable biometric data. If your camera is mounted 30 feet up on a pole looking down, facial recognition becomes basically useless.
And the moment you implement this, you have to confront these immediate, serious privacy concerns and regulations that strictly control how it can be deployed and how the data is handled.
It's a legal minefield you have to navigate very carefully.
Similarly, license plate recognition, or ANPR, relies on a separate technology but demands similar precision in the camera setup.
LPR relies on optical character recognition, OCR. The software is literally reading the characters from the plate image. The application is clear. Automated gate entry, parking management, monitoring for unauthorized vehicles.
But accuracy hinges entirely on the setup.
Completely. On-camera positioning, lighting, and angle. The camera has to be angled to minimize reflection and glare, and it often must be synchronized with a dedicated IR illumination system to capture the plate perfectly, especially at speed. Otherwise, the OCR will fail.
And this next generation of intelligence, it requires a radical upgrade in processing power. We're talking about deep learning classification.
Yeah, we've moved way beyond simple pixel counting or motion detection. Modern analytics use advanced AI models called convolutional neural networks, or CNNs.
And these are trained on?
On vast data sets, millions of images. They're trained to accurately classify objects with very high confidence, distinguishing a bicyclist from a motorcycle or a person from a large box that's being delivered.
This leap in accuracy is invaluable, but it must come at a cost.
It demands significant processing power. And that's why you often see requirements for specialized hardware like GPUs, graphics processing units, either on the edge devices themselves, in the cameras, or in dedicated analytics servers on the back end. This processing requirement significantly increases the hardware cost of the system.
Let's finalize this section with perimeter and intrusion detection.
So perimeter protection uses analytics to monitor fence lines and boundaries, often involving those virtual tripwires we mentioned. They can be set at varying heights to detect climbing over or crawling under a fence.
And we have to reiterate here, the effectiveness is maximized when you combine it with other sensors.
Always. You combine the video with thermal or radar sensors. That sensor fusion provides the necessary verification to reduce false alerts from wind or debris, making the security staff actually trust the alarms they get.
And what about loitering detection?
That's a crucial one for specific scenarios like banking or high-value retail. It identifies people who remain in a vulnerable area, like near an ATM or a loading dock, for longer than a predefined threshold. It's a great early indicator of suspicious activity.
And critically, none of this advanced AI works right out of the box. You can't just plug in a generic model and expect it to work perfectly.
That's the management burden that people forget. AI models require extensive training on site-specific footage, we call these training data sets, to understand the unique environment, the lighting quirks, the specific traffic patterns of that particular location. You have to continuously tune the detection thresholds and refine the algorithms to achieve optimal performance.
Otherwise, you spend all your operational budget just responding to alerts that tell you the sun came up differently this morning.
Exactly.
We've analyzed the hardware and we've analyzed the intelligence layer. Now we have to look at the whole picture. The true value proposition of modern CCTV is really realized when it stops being this siloed video archive and becomes integrated with the larger facility ecosystem.
This is the path to enhanced situational awareness and real operational efficiency. Integration means the systems are actually talking to each other, sharing data, and providing context for events.
So let's look at the most common and practical applications, starting with linking security systems. Specifically, access control verification.
This is a classic one. When someone presents an access card at a door reader, the VMS should provide visual identity verification in real time.
So the camera near that reader is automatically pulled up on the operator's screen.
Right, to confirm the person presenting the card actually matches the photo and identity linked to that card in the system. This is essential for auditing, and it helps prevent card sharing.
And that leads to a very clever use of analytics. Tailgating detection.
Yeah, this is a great one. If the access control system registers one credential presentation, but the camera analytics detect two or more people passing through the door, The system instantly flags a security breach. It closes a massive vulnerability in physical security.
Equally crucial is the link with intrusion alarm systems. If a motion sensor or a door contact is tripped, the security team doesn't want to waste time trying to find the right camera feed manually.
Integration is absolutely mandatory here.
Hmm.
When an alarm is triggered, the VMS must automatically display the video feed from the camera covering that exact triggered zone.
So it provides immediate visual context.
Immediate. It allows operators to rapidly assess whether the alarm is a genuine threat, a shattered window, or if it's a false activation, like a cleaning crew mistake. And they can do that before dispatching staff. That assessment capability saves critical time and resources, especially in large facilities.
Integration also extends to emergency coordination. Connecting with fire alarm systems seems logical.
It is, especially for post-incident review and analysis. The VMS should be configured to record evacuation routes and crowd movements to help authorities track the progress and identify choke points for future planning.
And more proactively.
More proactively, new systems are employing smoke detection analytics. They can identify the specific visual signature of visible smoke in the video streams. This can provide an early warning, potentially minutes before a standard heat or ionization detector activates, especially in large, open-air environments like warehouses or atriums.
Beyond pure security, how does CCTV integrate into broader facility management?
We're seeing a lot more integration with building management systems, or BMS.
So if a temperature sensor spikes in the server room,
An operator can immediately pull up the camera feed to visually inspect the equipment. Is there actual smoke coming from a server rack, or is it just a sensor error? This visual confirmation allows for a rapid, targeted maintenance response without immediately sending an expensive technician to investigate what might be a false positive.
and the same would go for confirming the status of lighting, power, or critical infrastructure systems.
Exactly. SCADA systems, for example.
And for crowded public spaces, the ability to communicate directly is incredibly powerful.
Integrating with public address and voice alarm, or PADA systems, is essential for coordination. Operators can quickly assess crowd conditions via camera before broadcasting announcements. They can ensure the message is delivered effectively and avoids creating panic.
And what about two-way audio?
Even more directly, two-way audio integration, where operators can speak through camera-mounted speakers, is a really effective tool for real-time de-escalation. You can warn an intruder that they have been spotted, or you can provide clear verbal instructions during an evacuation.
The ultimate synthesis of all these different systems is the unification layer. And the primary tool here is the Physical Security Information Management Platform, or PSIM.
PSIM platforms are designed to set above all the individual security silos: the surveillance, the access control, the fire systems, the intrusion alarms. They aggregate all the data, they normalize it, and then they present it in a single, unified, intuitive dashboard.
Often on geo-referenced maps or large video walls in a command center.
Exactly. The PSIM is the coordination engine that enables truly comprehensive situational awareness. It turns all that disparate alarm data into a coherent, prioritized operational picture for the security team.
But how do we ensure all these different products, a camera from one vendor, a VMS from another, and an access control system from a third, can actually communicate effectively with each other?
That's where the ONVIF standard is the critical glue that holds it all together. ONVIF promotes interoperability. You can think of it as a universal translator for security devices that prevents vendor lock-in.
So when you're purchasing equipment,
You must insist on specific ONVIF profiles like Profile S for basic video streaming or Profile T for analytics metadata. That guarantees standardized communication protocols. It simplifies integration projects, and crucially, it avoids the severe future costs and risks that come with being perpetually dependent on a single manufacturer's proprietary ecosystem.
okay, this final massive section covers everything that dictates the longevity and the legality of the system. Because poor implementation of excellent technology is still, at the end of the day, poor security.
It is. It doesn't matter how good the camera is if it's pointed at the wrong thing or installed improperly.
So we have to start with design and commissioning best practices.
The primary tension in design is always camera placement. It's this constant balance between achieving broad overview coverage and capturing sufficient facial detail for identification.
So a high-mounted camera gives a great overview of a parking lot, but it makes identifying a specific person very difficult.
Exactly. So your critical areas, like your points of ingress and egress, they require dedicated cameras mounted at optimal heights for identification, while other cameras can handle the broader overview.
And the goal must be to eliminate any and all blind spots, right?
Absolutely. The design requires overlapping coverage so that if one camera fails, the adjacent camera still captures the scene. Or if an intruder passes directly under a camera, the next camera in their path captures them.
And this isn't theoretical. The system has to be validated.
It does, with rigorous site surveys and validation. You must run test recordings and mock scenarios, have people walk through the scene at night, test the WDR against the morning sun. You have to ensure the system captures the required detail and meets the specific security objectives before the project is signed off and paid for.
And what about the necessary but unexciting element of documentation?
Handover documentation is absolutely non-negotiable for system longevity and for reliability. It must include precise as-built drawings showing exactly where everything is placed. It needs full configuration files and detailed network diagrams.
Why is that so important?
Because without this documentation, future maintenance or expansion or, critically, troubleshooting, a network bottleneck becomes exponentially more difficult and expensive because nobody knows how this system was originally wired or configured.
Okay, moving to operational maintenance. Our sources stress that this needs to be proactive, not reactive. You can't just wait for something to break.
Preventive maintenance is the key to stability. This includes routine tasks like cleaning dirty lenses, which can seriously degrade image quality. It means inspecting mounts for stability, especially important after high winds. And crucially, performing regular firmware updates.
That last point is a massive cybersecurity vulnerability, isn't it?
It is. Outdated camera firmware is one of the most common entry points for network attacks. Organizations have to have a plan for this recurring patching cycle.
We also must consider life cycle management. Equipment inevitably becomes obsolete.
It does. Organizations must have a plan for end-of-life, or EOL, planning. They need to budget for a gradual, phased migration to newer technology to avoid those massive, unexpected capital expenses when the entire system suddenly fails or becomes unsupported by the manufacturer.
And once an incident does occur, the incident response workflow is paramount to ensuring the evidence is legally usable.
The workflow must be clearly documented. Operators need clear procedures for reviewing live video, for bookmarking the relevant footage, and this is the most critical legal component, meticulously maintaining the chain of custody during evidence collection.
What does that mean in practice?
It means clear log documentation of who accessed the footage, when they accessed it, when they exported it, and how it was transferred to law enforcement or legal counsel. If that chain of custody is broken at any point, the evidence may become inadmissible in court.
Now, for the critical analysis of the legal landscape: privacy, policy, and legal compliance. Because the system captures identifiable images of people, it falls under strict data protection rules like the European GDPR.
It absolutely does, and that creates a continuous legal burden for the organization. They must have a clear, justifiable purpose for the surveillance. They have to protect the captured footage as personal data, and crucially, they must adhere to the principle of data minimization.
And regional regulations like signage requirements vary widely.
They do. The surveillance program has to be constantly audited against these changing standards, not just at the time of installation. It's an ongoing process.
So if you're using these incredibly high-resolution cameras, you need tools to help you comply with those privacy obligations.
You absolutely do. We're talking about tools like privacy masking and redaction. Privacy masking blocks out sensitive areas in the live and recorded feed. It permanently excludes private spaces, like the windows of a nearby home or a bathroom door, from ever being recorded at all.
And redaction is for when you need to share the footage.
Exactly. It's used when footage needs to be shared, for example, with law enforcement. It digitally blurs the identities of innocent bystanders to protect their privacy, thereby supporting that data minimization principle while preserving the core evidence of the incident.
This all boils down to accountability. How do organizations ensure their human operators are being compliant and ethical, given the huge potential for misuse?
Governance is key. They need robust audit trails that log every single operator action, every login, every configuration change, every footage export. Management must regularly audit these logs to detect any policy violations.
And training is vital.
Specific ongoing training for operators on ethics and acceptable use is vital. They have to understand the legal consequences of misuse and adhere strictly to acceptable viewing policies. The human factor is, and always will be, the most sensitive vulnerability in the entire system.
Finally, we need to acknowledge the distinction in guidelines for public versus private CCTV deployment.
It's a big distinction. Private systems on private property have a lot of latitude, but public deployments, the ones run by city councils or transport agencies, they face much stricter regulations regarding necessity and transparency.
For example,
The sources emphasize that public-facing signage must not only inform people they're being recorded, but it must also clearly identify the organization that is operating the system and provide contact information for data access requests under laws like GDPR. Transparency demonstrates respect for privacy while maintaining security effectiveness. So to synthesize this entire deep dive, I think the core lesson is profound. Modern CCTV is a sophisticated, live sensing layer. It's actively interacting with its environment. It is not merely a passive recording device anymore.
Right.
And achieving that capability, it requires deliberate, complex architectural choices. Everything from the network isolation and the power budgeting, the sensor fusion, to the specialized storage architecture and the constant analytics tuning, and all of it has to be grounded in a strict and demanding compliance framework.
The critical choice, then, for any organization deploying these systems, it seems to hinge entirely on balancing that cutting-edge technology, the AI, the deep learning, the fusion sensors, with the necessary legal and operational necessities.
Particularly GDPR compliance and maintaining the inviolable integrity in the chain of custody.
Exactly. The system must not only deter crime effectively, but it has to ensure that every piece of captured data is usable, it's ethical, and it's legally sound. Which means the data management is, in the end, just as important as the image quality.
Maybe even more so.
And while AI and analytics promise to automate detection and streamline security, we must always circle back to the element of human control. The human element, in the form of operator training, ethical oversight, and policy adherence, it remains the weakest link. And it's the most critical factor in system integrity.
It is.
So the final provocative thought for you to consider is this. What steps must organizations take to ensure that people managing this surveillance are as robust, reliable, and ethically sound as the technology itself? Recognizing that technological advancement only increases the potential impact of human error or misuse.
It's the ultimate question of governance in the age of omnipresent data.
Thanks for listening. We will continue to talk about security and technology. See you in the next episode.